Yesterday we talked about waves, we talked about longitudinal waves, we talked about transverse waves, and we covered the universal wave equation. Okay? Remember that the universal wave equation says the speed of a wave is related to the wave's frequency and the wave's wavelength. Which one of those three properties can't change? Frequency can't change. That means that if a wave slows down, it has to get shorter, okay, by essentially the same factor. All right, so speed and wavelength can change. They change together. Frequency will not change. All right, so what we're going to look at today doesn't have a whole lot to do with that idea, although that's going to come up a lot when we start talking about wave behavior and standing waves and stuff like that later on, okay, but not as much to do with what we're doing today. All right, today what we're looking at is what happens when waves occupy the same space at the same time. Okay, remember that that's possible because waves are not matter. Waves are energy. Okay, they're a traveling disturbance, so they can overlap each other. And they can travel right through each other. And we'll pull up the slinky and I'll show you that on the floor again. Okay, so you can see what happens when waves do occupy the same space at the same time. Okay, they are actually completely unaffected after they occupy the same space. Now, when they occupy the same space at the same time, they do this. They interfere with each other. Okay, that's what interference is. Interference is the resulting waveform from two waves combining their energy in the same place. Okay, generally, that's not something that works well. Okay? We generally consider interference a problem, okay, something that makes things not work well. Okay? If you set up interference in the right way, it can actually work for you. It can actually make waves larger and increase the effective energy of the waves if you do it right. Okay? If it's just waves kind of randomly combining in the same place, then generally that's when we get the stuff we consider to be interference. That is, I'm talking on my phone and suddenly the person cuts out, or call drops, or I'm watching something on my Wi-Fi and it slows down and starts pixelating and getting choppy and glitching like crazy. Okay, those are all signs of interference that we typically associate. Okay, they're still mechanically the same, but their result is a bit different. A jammer works by essentially flooding an area with waves of all wavelengths, frequencies, things like that, in order to cause essentially an overlap with desired waves. Okay, when that happens, then your phone, for example, can't pick up, or it picks up the signal that's being sent to it, but it's so overwhelmed by the surrounding chatter, okay, that it can't decipher it anymore. Does that sort of make sense? Okay, so yeah, a jammer has to have a wide range of frequencies, wavelengths that it transmits on, okay, in order to essentially blanket it. Okay, so we're going to look at what happens when two waves occupy the same space. We're going to look at the two types of interference and understand how that can be applied to practical uses. Okay, most of our musical instruments actually rely on interference. And by musical instruments, I mean acoustic instruments, not electrically powered ones. All right, so if you play an acoustic guitar, for example, an acoustic guitar relies on the interference of waves both on the string as well as in the resonance cavity of the guitar to naturally amplify the sound. Okay, when you strum a guitar string, okay, if you have an electric guitar but it's not plugged in and you pick the string, does it sound very loud? Okay, but if you do that same action on an acoustic guitar, is it quite loud? It is. Okay, it's the same amount of energy. All we're doing is harnessing it all, making it interfere with itself. Okay, before exiting the resonance chamber in a much louder fashion than it went in. Okay, so that's kind of what we'll be looking at there. Most of our musical instruments rely on taking the waves and reflecting them back on each other, or on themselves, okay, in order to make them get bigger, okay, and thus sound louder. All right, so straightforward way to deal with situations in which two or more waves pass through the same place simultaneously. Okay, what we do is we essentially add their amplitudes together, because after all we're doing is combining the energy of the waves. So it would be natural to add the wave energies together. So if I have this situation here on the left where I have one pulse, okay, so this one here that's up, and this pulse that's also up, traveling towards each other, I have a certain amount of energy, wave energy, on that spring. When those two waves start to overlap, the spring has to reflect, and I don't mean like bounce off, I mean it has to show the energy of both waves at the same time. So instead of having two waves with an amplitude of, let's say, like +1, we now have a single wave with an amplitude of +2. Okay? That way all the energy that was on the spring is conserved and shown, okay, as they overlap. Now, once they travel through each other, because they are traveling in opposite directions, okay, they go on completely unaffected. Okay? They don't lose any energy in this because they are energy. They can't take each other's energy away by passing through each other. Okay? It's like if I shine two flashlights across each other. Okay? Where the beams cross, is it a little brighter? Okay? But after that, they're just as bright as they were before. Okay? They don't steal each other's energy as a result of crossing the beams. Okay? Wave energy works like that. Okay? The only reason the beams fade out is because they eventually get so wide that they their energy is spread out over too large an area to notice. Okay? All right. If I have waves that are opposite, okay, like in the situation here on the right, so I've got one wave with an amplitude of +1 and one wave with an amplitude of -1. When they overlap, I add their amplitudes together, and it looks like I have 0. Okay? The combined energies cancel each other out for a second while they're overlapping, and then they continue moving on just as they were before. Okay? But the spring shows the amount of combined energy anytime two waves overlap. Okay? They are either going to overlap this way, which we call constructive interference. Oop, got to spell constructive right. Whoa, that's big. Okay, or destructive interference. Okay, so if the combination of the waves results in a larger amplitude, it's constructive interference. If the combination of the waves results in a smaller combined amplitude, then it's destructive interference. Okay? Make sure you make note that it is destructive. There's no such thing as deconstructive. Okay? You either destroy or construct. You don't destroy and construct. That's what deconstructive is. Okay? Businesses. Get it? All right. Mr. Dickey and I took videos of our slinkies on the floor so we could slow them down and we could see this a little bit better. Okay, so we'll show you that here. Hopefully. Okay, so we got these two waves going towards each other, and when they overlap, you could see that for a second there was no amplitude. Okay. So if we just back it up a little bit here. Okay, so the waves are approaching each other. Okay, and then when they're actually completely overlapping, which is I guess right there, okay, we see an amplitude of effectively 0. And then those two waves continue to travel on unaffected, okay, afterwards. Okay, and then we have where we make them both to the same side, I think, here. Okay, so now the two waves are going towards each other, but they're both up. They're both in the same direction. Okay? Okay. See how the amplitude is now double? And then they go on completely unaffected after. Okay? It's way better than trying to show you this on the floor because it happens too fast. Okay? But here you can slow it down and actually see, right, the resulting action. Okay? Are you all right with that? Okay, so that's the two kinds of interference right there. All right, so in the diagram on the right, okay, that's where we're looking at, okay, constructive interference, okay, we add the amplitudes here on the left, destructive interference, we still add the amplitudes, it's just that one is negative and one is positive, so they cancel each other out, okay? So this principle of linear superposition, I know that sounds like a really complex thing, okay? Principle of linear superposition is this, okay? When waves occupy the same space, the amplitude of the medium is the sum of the individual waves. Okay, so the principle of linear superposition is basically just what happens when two waves are in the same place at the same time. What happens? What does it look like? Okay, so the way that I would test this on a unit exam, like say next Wednesday, okay, would be that I would show you two waveforms overlapping. And I would ask you to draw the resulting shape of the medium. Okay, so that might look something like, okay, so I would have, let's say a wave that looks like, okay, a wave that looks like that, and another wave that looks like that. Okay, what's the medium going to look like? Twice as big. Yeah, it's going to be the sum of those two things. So my resulting shape would look like this. Okay, that would be those two waves added together. Okay. All right. What if I made it just a little bit more complex? What if I did those two waves? Are they going to cancel completely? No. Right, one's bigger, the other is smaller. Okay, so let's say that this one's got an amplitude of +3, and this one's got an amplitude of -1, and then the opposite over here. Okay, my resulting waveform, if this is +3 and this is -1, this side's going to have an amplitude of 2, and over here, -2. That would be my resulting waveform. Okay, those waves occupy the same space at the same time. I add their amplitudes, I draw the resulting wave. Okay, what kind of interference would that be? Destructive interference. It made the amplitude smaller. Okay, I'm going to ask it just like that. How do I know that? Because it printed it. That's what I'm going to ask. Okay, just like that. You better all get that one right. Yeah. Now he says something else, yeah. Okay, so when two opposite pulses overlap, okay, like in the situation here on the right, then obviously they're going to cancel each other out. We saw that, okay? That's always as a result of this idea of the principle of linear superposition. Add the amplitudes together, and you're going to get the resulting shape. Okay, so this is kind of what I drew a minute ago, except it's better because I didn't draw it. Okay, when two or more waves are present simultaneously at the same place, the resultant wave is the sum of the individual waves. So, in this case here, okay, wave A and wave B are in the same place at the same time. They are also what we would refer to as in phase. Okay, and the reason we call them in phase is because when A is up, so is B. Okay, so they are in phase. They have the same wavelength, they have the same frequency, okay, they're going to be traveling at the same speed, okay, all that stuff along this medium, right? So as a result, since when this one is up, this one is up, when this one's down, when this one's down, I'm going to get what kind of interference? Constructive interference. Okay, so as a result, the resulting waveform, which is here at the bottom, is showing the sum of those two waves. Okay, the medium is moving a lot more, okay, as a result of those waves. Okay, if we're looking at the situation here on the right, okay, when wave A is up, wave C is down. Okay, these are out of phase. Okay, and they're out of phase because when one is up, the other is down, and that means that I'm going to get destructive interference. Okay, so my resulting waveform will look like this. Okay, and it'll be much smaller. Okay, sometimes we want to have constructive interference, like in a musical instrument where we want it to naturally amplify itself, and sometimes we want to use destructive interference to make something quieter. Okay, this is how a muffler works on your car. Okay? A muffler bounces the sound waves around inside it through screens, effectively decreasing their amplitude by making them go out of phase with each other, so that the sound of your motor doesn't sound like, you know, the redneck mobile. I don't know who drives it, but somebody goes by my house all the time with their redneck mobile. You know, the ones with the exhaust is chopped off right past the headers. You know, it's got no catalytic converter. Okay, that guy. Okay. All right. Does this idea of constructive and destructive make sense? Yes. Okay. Now, more practical application stuff. What are some ways I can use this to my advantage? Well, one of the ways I can use this to my advantage is I can use sound waves and the fact that they interfere with each other to make places that are naturally amplified. They're areas of natural amplification. Okay? I don't need to necessarily make any extra power. I'm just going to have waves that are louder. Okay? If you go to very well-designed concert halls, okay, they typically will do this. How many people have ever been to the Winsphere Center in Edmonton? Okay, nobody. Okay. The Winsphere Center was built in the 90s. Okay, but it's effectively a concert hall, but it is so acoustically perfect that it requires very little powered amplification of anything. So if there's a concert there, okay, but essentially the people don't need to have microphones, okay, nor do the people playing the instruments. It can be done almost entirely acoustically and sound good almost anywhere in the hall. Right? You go and watch a concert at the Saddle Dome, it's terrible, okay? And it's just really loud because they put speakers everywhere, because acoustically the design of the Saddle Dome is as loud, as bad as it can possibly be. Okay, there's no, all the stuff just reflects randomly off all these different surfaces. Okay, and the only way to make it sound half decent is just to have it be really, really loud. Okay, but if you go to a place that's designed just for music or things like that, then you're going to find a place that's going to be more acoustically perfect, okay, than a place like the Saddle Dome. Right? So here's what I can do if I want to have these areas of natural amplification. Okay, if I make sure that my sources of sound are in the right position, I can make it so that at certain positions it's going to be louder by making sure constructive interference occurs where I want it to. So for these two speakers, okay, the distance the waves have to travel to the observer is the same distance. That means it's the same number of wavelengths from the speaker to the observer. And so the wavelengths, the waves coming from both speakers are going to arrive in phase with each other because they've traveled the same number of wavelengths. As a result, we're going to get constructive interference. Okay? So if you see the diagram here, the dotted lines would be troughs, and these lines here would be crests. Okay? Remember we talked about that the other day? Actually, with a longitudinal wave, it's a compression and a rarefaction, Okay? But you can see here at the observer, they're overlapping in phase. It's a compression to a compression, and this person would hear a loud sound. Okay? Effectively, what we're seeing is, okay, waves from this speaker are coming in like this, and waves from this speaker are coming in exactly the same way. Okay? They're coming in both in an upward position, and so their amplitudes will add together and make a louder sound. Okay? Now, if this person moves from this position, will the sound change? Yes, it will. Okay? Because as soon as they move, now the number of wavelengths from each speaker is different. And as soon as it's different, they may not be arriving in phase anymore. In fact, if they step to the right place, they could move to a place where they would hear no sound at all. It's pretty tough to actually do that, okay? Because you'd have to have a room in which there are no echoes. Okay? Sound could not bounce off the walls. Okay? If that was the case, then you would actually be able to walk around the room, find places where it's silent, and places where it's loud, and places in between. Okay? But you'd actually be able to do that if you were in what's called an anechoic chamber. Okay? They actually have these, but they're scary. They look like something out of a horror movie. It would be like what it would look like if you were inside of a meat grinder. Okay, that the walls have all these weird sharp edges and points and stuff like that in order to make sure echoes don't come off a flat surface like they do in here. Okay? Ever notice how when you hear yourself, you sound different? Like if you hear a recording of yourself, you sound different than what you sound in your own head. Okay? The reason for that is the sound you hear of yourself is a combination of the sound resonating and reflecting inside your own head, as well as the reflections off of other places. Okay, so when I hear myself in here, I think I sound pretty good. Okay, so I hear the echoes off the walls and I hear the sound in my own head. And then when I listen to one of these podcasts, I'm like, those poor kids who have to listen to that person. Okay, it sounds a lot different. Okay, you hear it right from my mouth. It sounds a lot different than what I hear. Okay, so what we see, okay, with these two speakers or two sources of sound is each one produces waves. If I'm standing right here, what will I hear? I'll hear loud or quiet? Loud. Okay? They're meeting crest to crest. What if I stand right here? Actually, right there, I'll hear nothing at all. Okay? See how I'm on a crest from speaker B, but I'm halfway in between the crests from speaker A. In other words, I'm at a trough. Here. Okay? That's the exact opposite of the crest that came from B. So that would be an area of complete destructive interference. Whereas if two lines are overlapping, that's an area of constructive interference. If I was standing right here, what would I hear? Loud. Because that would be two troughs. So that would be a loud sound as well. Okay? As long as I'm standing in a place where the waves arrive in phase, okay, then I'm going to hear a loud sound. Okay? Now, what if I back this up? Okay, I back this person up so that they're now still 3 meters from this speaker, but they're 3.5 from that one. Now what will they hear? Okay, they might hear a little more from the left side, but if I move them another 0.5 meter, how many wavelengths further is the wave traveling from the other speaker? 1/2 a wavelength. Okay. Now, if it's got to travel an extra 1/2 a wavelength, now they're not meeting crest to crest; they're meeting crest to trough. Okay, because a crest and a trough are always a 1/2 a wavelength apart. At that position, the person would hear nothing at all. Okay? What if I backed it up so that they were 3 meters from this speaker and 4 meters from that speaker? And they would hear loud. Let me show you. Okay? So I'm going to move 1, 2, 3, okay, from this speaker, and 1, 2, 3, 4 from this one. That's right there. Okay? That's still me hearing a loud sound. But if I'm 3 meters from this speaker and 3.5 from this one, that's right there. And now I hear nothing. Okay. All right, so this example is showing constructive interference because the waves are exactly in phase with each other. Okay, that's going to be constructive interference. Okay, this is the situation I was telling you about just a second ago. Okay, if I move this person so that they're 3 meters from one but 3.5 from the other, now they're meeting crest to trough. Okay, this one travels 3.5 wavelengths and arrives as a trough. This one travels 3 wavelengths, arrives as a crest. That's out of phase, so I get destructive interference. Okay, so you kind of have to remember, when we're looking at a wave, okay, so this is one full wavelength, okay, that a crest and a trough are exactly 1/2 a wavelength apart. Okay, everybody with me on that? Okay, so if they're arriving like that, 1/2 a wavelength difference, then you're always going to get destructive interference. All right. So in general, the thing that determines whether you have constructive interference or destructive interference, or whether you hear a loud sound or a quiet sound, is the number of wavelengths traveled from each source. Okay? If the difference in wavelengths is a whole number, 1, 2, 5, 10, they're still going to be arriving in phase, and you'll still hear a loud sound. if the difference in travel is a half a wavelength, so 1.5, 3.5, 10.5, then they're arriving out of phase, and that would be destructive interference. Okay, and that person would hear a quiet sound. So again, there it is, looking at it from these speakers here. Okay, at this red dot here, waves from this, there have been 2 waves from this speaker, 1, 2, and there have been 1, 2, 3 from this speaker. Okay, 3 minus 2 is 1. That's a whole number. That's in phase, crest to crest. Okay, if I'm looking at this position, okay, this hollow dot here, okay, then I've traveled 1, 2.5 wavelengths from this speaker, but 3 wavelengths from this one. 3 minus 2.5 is 1/2. They're arriving out of phase, and it's destructive interference. Okay? So basically what I have to be able to do is figure out how many wavelengths have the waves traveled from each source, and then I'll be able to figure out if it's constructive or destructive interference. Right? That's going to require me, most likely, to use the universal wave equation, at least at some point. Okay? All right. I want you guys to copy this example down. We're going to go through it here. Okay, so copy this one down, including the diagram. This is exactly how I will ask an interference question, okay, on an exam. Right, so this is a good example. I want you to copy it down, and then we'll walk through it together. Okay, so as we were saying just a minute ago, the thing that determines whether constructive or destructive interference occurs, whether they hear a loud or no sound at all, is how many wavelengths are traveled from each speaker. Right? So I need to know how many wavelengths there are between this speaker and the listener, and how many wavelengths there are from this speaker to the listener. Okay? So if I'm going to figure out how many waves there are in 2.4 meters, what do I need to know about the wave? Okay, I know its frequency, its length. Yeah, I need to know how long one wave is so I can figure out how many waves there are in 2.4 meters. So I need to calculate the wave's length. Okay, I need to know what lambda is. Okay, I don't have it right now, but I have the speed of the waves, 343 meters per second, and I have the frequency of the waves, 214 hertz. Okay, so I'm going to calculate wavelength using the universal wave equation by going V over F. Okay, so 343 divided by 214 should be 1.6. Yeah. Okay, so each wave is 1.6 meters long. Each one of the waves produced by these speakers is 1.6 meters in length. So, can I figure out how many waves there are between the speaker and the observer, at least on this side right now? Okay, how do I do that? Divide, yeah. Divide 2.4 by 1.6. That'll tell me how many waves there are. Okay, well 2.4 divided by 1.6 should be 1.5. Okay, so that means there's 1.5 wavelengths. So it would look something like this. There's one wave, and there's a half a wave. So it's arriving at a crest, okay, from that speaker. Everybody all right with that? All right. If I'm going to do the same thing from this speaker to this speaker, I need to know how far it is to the speaker from the person. Can I figure that out? Okay, that's what the Pythagorean Theorem thing is all about there at the bottom. Okay, I'm going to use Pythagorean Theorem to find how long this side is. All right, so I'm going to take 2.4 squared plus 3.2 squared, okay, and then that side's going to be exactly 4 meters in length. Okay, now same waves, okay, it did make a point of saying that it's the same waves from each speaker, so I'm going to do the same thing. I'm going to go 4 divided by 1.5. Okay, what's 4 divided by 1.5? 2.5. Okay, so 4 meters divided by, 1.6. Sorry, that should give me, 2.5. Okay, so from this speaker, waves are doing, so there's 1, there's 2.5. Are they arriving in phase? Yeah, they're both arriving as a crest at that person's head because I've got 2.5 waves from this speaker minus 1.5 waves from the other speaker. That gives me a whole number, 1. Okay? Anytime the difference is a whole wavelength, then they're arriving in phase, and I will hear a loud sound. Please, questions?
Does the wave always start with a crest going up? Or?
It doesn't have to. I just drew it that way. It could have started with a trough, and then it arrived trough to trough.
Okay. But what if the left one started with a trough and the right one started with a
It wouldn't. They're producing the same sound at the same time.
Okay.
Okay, now, you're going to get a problem like this on your unit exam, just so you know. The question will ask, do you hear a loud or quiet sound? Understand that since you could guess the answer and have a 50-50 chance of getting it right, that will not get you full marks. Okay? If all you write is loud, knowing you had a 50-50 chance of getting it right, you have a 50-50 chance of getting 1 mark on that question. You do have to have proof. There. I need to see your work so that I know you didn't just guess. Okay? Everybody with me on that one? All right. Does what we did there make sense? You will be asked to repeat. All right. So, what I'm going to have you guys do now is I want you working on a couple of things here to do with the universal wave equation because we didn't get a lot of time on that yesterday. Okay, so we're going to do a couple things to do with that, and then we might move on to wave behavior here. Okay, that for some of these, you're going to need to remember that electromagnetic waves, radio waves, light waves, all travel at what speed? Speed of light, 3.0 times 10 to the 8. Okay, sound waves. Okay, you might have to use that 332 plus 0.6t formula that's on your formula sheet to calculate the speed of the sound waves. Okay, remember that frequencies that are given in megahertz, that's 1,000,000 hertz. Okay, or kilohertz is 1,000 hertz. Okay, things like that. So just be aware of those units. Okay, that you might run into on some of these questions. All right, so let's get to that, and I'll circulate. If you need some help, I will help you out. All right, so with number 11 here, okay, we have sound traveling at a speed of 343 meters per second in air at 20 degrees Celsius. Did they need to give you the temperature? No. No, they already told you how fast it was going. It's just there to throw you off. Okay, we know the speed is 343 meters per second. We know the wavelength of that sound wave is 1.31 meters. Okay, we're trying to find the period of that wave. Okay, well remember, this universal wave equation can be written like this or like that. Okay? Now you could just solve for frequency and then go 1 over that as well, but okay, it's just as easy to do this. So T will be lambda over V. Okay, that'll be our 1.31 divided by 343, and that should give us the period of the wave being 3.81 times 10 to the minus 3 seconds.
When you know that when you use the one formula,
If they give you the temperature of the air and not the speed.
oh,
Okay, so it says a sound wave traveling through air at 25 degrees Celsius. Frequency is this, calculate wavelength. Then you'll have to use that to get V, so you can use it without the Yeah? Okay. All right, then we're going to move on here, guys, if there are no more questions. 9? Okay. Okay, so number 9 is just a metric conversion question here, guys. Okay, if I've got 0.652 micrometers as a wavelength, okay, then my wavelength is 0.652 times 10 to the minus 6 meters, because 1 micrometer is 10 to the minus 6 meters. Okay, so I have that, and I have the speed, which is 3.00 times 10 to the 8 meters per second. So I'm looking for the frequency of the light in hertz and in megahertz. Okay, well, if I've got this in meters and this in meters per second, when I find the frequency by going V over lambda, okay, then I'm going to have, this is going to come out to hertz because the meters will cancel. So I'll have my 3.00 times 10 to the 8 divided by 0.652 times 10 to the 6. That should give me 4.6 times 10 to the 14 hertz. Okay, when I do that. Now, there are a million hertz in a megahertz. So I take that number and divide by a million, and I get my megahertz, which is why it's 10 to the 6 smaller than that number. Okay? Everybody with me on that? It's just a metric conversion question. Okay? Just got to know our metric systems. Okay, any other ones? All right.
That's it. We're going to move on here.
Okay.
Okay, so we're moving on to lesson 14, which is wave behavior. Now, there's going to be some stuff in here that's going to relate to interference, as well as a bunch of stuff from the properties of waves lesson. Okay, and a few things from the universal wave equation. So, some quick things to review about waves. Okay, first off, they're traveling disturbance. Okay, don't forget that. The speed of a wave changes, then the wavelength has to change, but the frequency doesn't. That's going to be important here. Okay? When a wave moves from one medium to another, then speed and wavelength will change. Okay? That is when speed and wavelength change. Okay? Whenever there's a change in one of those two properties of a wave, then the other one has to change as well. And so what we want to look at is what happens when a wave encounters the boundary between two media. Okay? Understand that while many characteristics of a wave change when it enters a new medium, frequency doesn't. Okay? And learn what happens when the properties of a wave change. Right? So we said that if we have like water waves moving in the ocean towards the shore, that as they approach the shore, they slow down. When they slow down, they get taller and shorter. Now, I know that doesn't make sense because tall and short are opposites, but I mean short in terms of length, taller in terms of amplitude. Okay? So their wavelength decreases because their speed is decreasing. If their speed is decreasing, then the kinetic energy is going to be decreased. But energy has to be conserved, so the wave gets taller to increase its potential energy. Right? That's how energy gets conserved in a wave as it moves. Right? So that's kind of what we'll be looking at here. All right, so waves can travel through lots of different materials, but when it goes into a new material, it changes its speed. Okay? So when light passes from one material or medium to another, its speed changes. This speed leads to a change sometimes in the direction of the wave, which is why we can bend light. Right? Which I'll show you here in a minute. Okay? If I have like a laser, okay, going into another material from air, its direction will change. And you can see that here. Okay? This is our incident wave here. And then there's the refracted wave or beam, okay, in the other material. It's changed direction because in this medium it travels slower. Okay, so it bends. Right? Also, we can see that some of the light energy didn't actually go in. Some of it got reflected. Okay? That happens. Anytime a wave encounters a boundary, some of the energy will get through, and some of it won't. The energy that doesn't get through gets reflected. Okay, so anytime light or any other wave encounters a boundary, some of it will get in, we call that transmission, and some of it will get reflected. Okay, we call that reflection. Everybody follow me on that? Okay, so I'm going to show you that here real quick. Okay, Ben, I'll get you to turn that down for you. Thank you. Okay, so we're going to look at very simple waves first. We call these one-dimensional waves. Okay, that would be like if I made waves on a slinky or a rope or in a hose or something like that. Those are one-dimensional waves. Okay, so wave energy that's incident on a boundary between two media can either be transmitted to the next medium, reflected off the interface, or both. Okay, most of the time it's both, unless the boundary is actually not a boundary but a barrier. Okay? If it's a barrier, then the waves don't get into it. All right, so if I was to, let's say, tie a rope to the door, for example, to the handle of the door, okay? When the wave travels through the rope, it's not going into the door. It's just going to bounce off the door and come back to you, okay? It's what we call a fixed end or a barrier, okay? The wave's not traveling into there. And most of the time, though, we have both incidents happening. Now, this is something you have to kind of memorize, okay? But in this first case here, I've got a more dense medium followed by a less dense medium. I have a pulse that's up, traveling towards the less dense medium. Now, when the wave gets to the less dense medium, it can travel faster because this medium is less dense. It's easier for the wave to travel in it. Okay? So some of the wave energy gets through, most of it. Okay? But some of it reflects back, and that reflection is upright. Okay? The transmitted wave always looks like the incident wave. It's always upright. Okay? The reflected wave can reverse depending on the situation. Okay? But in this case, okay, I've got this transmitted pulse going through. Now, that transmitted pulse is longer. Why is it longer? Because it's going faster. Okay? When the front of this wave up here encounters the boundary, it speeds up and runs away from the back of the wave, stretching it out. Okay? That's why when speed increases, wavelength also increases. They are affected in the same way at the same time. Okay? So it gets longer, okay, and faster. And it's not quite as tall either. Okay? Because it's kind of stretched out. Make sense? Okay. We're going to talk quite a bit more about this tomorrow. Okay? Like most of the class will be on wave behavior, and there's some really important stuff you'll need to make note of to do with this.
Yeah.